Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 3450 Mission to Mars, Lecture 3, Gravity. In our last lecture, we talked about Newton's laws of motion and how they apply to spaceflight. In this lecture, we're going to talk about Newton's law of gravity and how that applies to spaceflight. And there are a couple different concepts we'll talk about: weight and mass. We'll talk about Newton's law of gravity, we'll talk about weightlessness, and then we'll talk about orbital velocity and escape velocity. So the first thing I want to talk about is the difference between mass and weight. Mass is a measure of the total amount of material that's in an object. So for example, you can talk about the mass of your body, and whether you're on the surface of the Earth or on the surface of the Moon or you're off in deep space, the mass of your body is the same. Mass is a measure of the resistance, and we call that resistance inertia. It's a measure of your resistance to changes in motion or accelerations. You can imagine that if I have a body moving in a straight line at a constant speed and I want to change its motion, move it in a different direction, I have to apply some force to it, and it resists that force. And that resistance is the inertia of a body. Maybe the place where inertia is most famous is when a body is at rest. You have to push it to get it going. And that resistance to getting going is the inertia of the body. And mass is a measure of the inertia. The property, it's also the property that gives a body weight in a gravitational field. So I'm here on the surface of the Earth. I have some weight, and my weight comes from the mass in my body. Now, in the metric system, in the International System of Units, we use the kilogram for the unit of mass, and we will be using that throughout this semester. Anytime you need to plug mass into an equation, in any equation this semester, that mass should be expressed in kilograms. The other one that you might see on occasion are grams. And just remember that there are 1,000 grams in a kilogram. So if I give you a mass in grams, you need to divide by 1,000 to convert it to kilograms. So that's mass. Weight, on the other hand, is slightly different. Now, in our everyday lives here on the surface of the Earth, we use mass and weight interchangeably. But in physics, we're careful to differentiate the two. So mass was the measure, a measure of the amount of material in a body. Weight is the amount of force that the body applies. And typically, when we talk about that force, we're talking about the force of gravity here on the surface of the Earth. So for example, my body, the mass of my body is a certain number of kilograms, but the force of gravity pulling me down to the surface of the Earth exerts a force on the surface of the Earth, and that force is my weight. Now, in the metric system, the unit of weight, or the unit of force, is the Newton. In the English system, the pound turns out to be a unit of weight. Now, we always talk about it as if it's a unit of mass. When you get on that scale in the morning to measure your weight, you're truly measuring the force that you're pushing down on the scale. What you're really trying to get at there is your mass, how much material is in your body, and you're doing that by measuring your weight. But in the English system of units, pounds is not a unit of mass. It turns out the unit of mass is called the slug, which is a little bit more than 32 pounds, but we won't worry about that now. Just know that in the metric system that we'll be using, mass is measured in kilograms, weight is measured in newtons. Now, a mass of 1 kilogram produces a force, a weight of about 9.8 newtons on the surface of the Earth. And that means that an astronaut that weighs about 100 kilograms produces a weight of about 980 newtons on Earth. But this weight depends on the force of gravity. And the force of gravity is different on different bodies. As we'll find out later in this lecture, the force of gravity on the Moon is 1/6 the force of gravity on the Earth. So that same astronaut that weighs 980 newtons on Earth only weighs 162 newtons on the Moon. Now, I know many of you grew up using pounds, and so just very quickly, because that's an interesting one to go over, that means that if you weigh about 220 pounds on the Earth, you only weigh 37 pounds on the Moon, 1/6 as much. So that raises the interesting question: why are astronauts sometimes weightless? This is an image taken from STS-126. That's the 126th flight of the space shuttle. You see two astronauts floating on the middeck of the space shuttle. This is the lower deck on the space shuttle. and they're just floating. And you can see that there's a whole bunch of fruit in front of them, some pears and apples, looks to be some oranges, and they're just floating there weightless. Why are things weightless in space? Why are astronauts weightless in space? To show you how fun it is to be weightless, I've got a couple quick clips of video here from Suni Williams. She has been on the International Space Station a couple of times, and she's actually going to fly again here in space relatively soon. But here's her giving a tour of the International Space Station, and you'll see how much fun it is to be weightless.
Hello, I'm Suni Williams. I'm up here on the International Space Station. It's like a glass-bottom boat. This is the cupola. It sticks down below the space station. It's one of those places you find yourself hanging out in all the time because all you want to do is look back at our planet. I think some questions I had were about what do you do in your free time? And you can't help but want to just come to the cupola and look outside as much as you can. And a lot of folks, I play this game with myself about where we're flying over the Earth. Try to come in here and just guess. After being here for a little while, you can sort of figure it out. You can tell different cloud types over different continents. You can tell different soil types over different continents. So let's see. And then, of course, there's a lot of ocean. So usually we're over the ocean at first glance. I will tell you in just a moment where we are. There we go. Oh, right now we are right over Africa. It's a little bit cloudy, as you can tell.
All right, let me show you another quick clip here about what it's like to be weightless.
Hey, Aki, what are you doing down there?
Crashing things.
This is one of the cool things about space, too. It sort of looks like there's a big old hole here, but you don't even think twice about it. You can just jump over the hole, or if you want, you can go jump into the hole. I'm coming down. Woo! Then you can come right back up again, like Superman. Woo! We're lucky we have a really cool big space station that you can fly around in. That's actually called the PMM. You might have saw it out the window. It's a big silver canister.
So we'll see more about the International Space Station later in the semester when we study the International Space Station, and you can watch Suni Williams's full tour then of the International Space Station. So the question I have for you right now is, out in the lecture exercises, is astronauts inside the space station are weightless? What is the force of gravity acting on the astronauts when they're weightless? So this is a good time to pause the lecture, go out to the lecture exercises, and go ahead and answer this question. Is the force of gravity on an astronaut when they're weightless, is it exactly zero? Is it very much less than when they're standing on the Earth? I mean, almost zero, but not exactly zero. Is it about the same as when they're standing on the Earth? Or is it much more than when they're standing on the Earth? So go out and just, what do you think on this one? What do you think is the answer to why astronauts are weightless? All right, welcome back. What did you think on this one? I'll give you the answer to this one in just a second. But to help you try and figure out the answer to this one, I want you to go back out to the lecture exercise and I want you to answer this question. What holds the moon in orbit around the Earth? Or what holds the space station in orbit around the Earth? That is, why does it not just fly off into space? If you think about the space station for a second, the space station's about the size of a commercial airliner. Actually, somewhat bigger, I should say. It's about the size of a football field, somewhat bigger than a commercial airliner. And it's flying at 17,150 miles an hour, 7.6 kilometers per second as it orbits the Earth. Why doesn't it just fly off into space? What keeps it in orbit around the Earth? Is it gravity, A? B, is it that its speed allows it to keep up with the Earth as the Earth orbits the Sun? C, its velocity allows it to keep up with the Earth as the Earth orbits the Sun? D, all objects must orbit or they will fall together? Or E, is it rubber bands? Lots of them. So go ahead and answer this question out there on the lecture exercise. All right, so what did you get for the answer for this one? Well, the answer for this one is pretty obviously gravity, right? It is gravity that holds the moon in orbit around the Earth. It is gravity that holds the space station in orbit around the Earth. Now, think about the moon for a second. The moon is a few thousand miles across. It is a massive ball of rock, and it is moving very, very quickly. And if you think about the moon for a second, there must be a tremendous amount of gravity that's holding the moon in orbit around the Earth so that the moon doesn't just fly off in space, because you've got this huge ball of rock and it's moving very, very fast. The force of gravity holding it in orbit is tremendous. And the same is true with the space station. The space station doesn't fly off because there's no gravity. The space station is held in orbit around the Earth because of gravity. And that gets to this question. A common misconception is that astronauts are weightless because there's no gravity in space or there's very little gravity in space. And in fact, that is not at all why they are weightless. We'll see later on in this lecture why it is that they're weightless. Turns out the right answer to this one is C. The force of gravity acting on the astronauts when they're in orbit around the Earth is about the same as when they're standing on the Earth. The reason that they're weightless is not that there's no gravity acting on them. Again, if there was no gravity acting on them, according to Newton's first law, they would fly off in a straight line at a constant speed. The reason that they're weightless, we'll see later on, is that they're falling. So let's talk about the force of gravity for a few minutes. So here's this misconception, just to address it. The misconception is that astronauts are weightless because there's no gravity in space. And as we've seen, it turns out it's gravity that holds the International Space Station in orbit. It holds the moon in orbit. It holds the Earth in orbit around the sun in orbit around the center of our Milky Way galaxy. It's pulling our Milky Way galaxy and the Andromeda galaxy together. So there's lots of gravity in space. In fact, the force of gravity is infinite in extent. As we'll see here in a second, when we look at the equation for the force of gravity, as far away as you go, gravity never falls to exactly zero. So what is the law of gravity? The law of gravity is called Newton's law of gravity, and it was worked out by Isaac Newton in a period of about 2 years from 1665 to 1667. Newton had just finished his bachelor's degree at Trinity College in Cambridge, and the Great Plague shut down Trinity College, and so Newton had to return home. And during these 2 years that he was home, because of this plague, he worked out many of the basic laws of physics, and one of those that he worked out was the force of gravity. And we call it now today Newton's law of gravity. And there it is in front of you. Newton's law of gravity says that the force due to gravity is some constant, g, times the mass of the first body times the mass of the second body divided by the distance between the two bodies squared. And we'll get into this here in more detail in a second. But the important thing to know about it is when I talk about the law of gravity, I'm using law the way scientists use the term law. What we mean by a law in science is something that describes. And this describes how the force of gravity depends on the mass of the two bodies that are attracting one another and the distance between them squared. Now, what it doesn't do is it doesn't explain why we have gravity. Newton tried to figure that out, and Newton was never able to do that. The law of gravity does not provide an explanation. The things in science that provide explanations are called theories. And when we use the word theory in science, we're not using it in our everyday terminology. In our everyday lives, the word theory means something that's speculative. I'm not quite sure about it. My theory is, in Old Mysteries, my theory is that the butler did it. I don't really know who did the murder, but I think it was the butler. That's not what we mean in science. In science, when we use the word theory, we're talking about something that explains. Now, Newton came up with his law of gravity, which describes the strength of gravity, but it was Albert Einstein who developed his theory of relativity, in particular his general theory of relativity. And he developed that from 1907 to 1915. And that provides the explanation behind gravity. Now, Albert Einstein taught us that gravity comes about because mass warps the space and time around it. And by warping, I literally mean bending the space-time around it. And here's the thing. It not only bends space, but it bends time as well. Now, Einstein's theory of relativity, his general theory of relativity, is a much better description of gravity than it's a much more accurate, I should say, description of gravity than Newton's law of gravity. The thing is, we generally don't need to use it in spaceflight. Because first of all, Einstein's general theory of relativity is far more complex. The mathematics are much more difficult. But the other thing about Einstein's general theory of relativity is it's really only important in very specific cases, typically when masses get very, very large. So for example, in astronomy, the general theory of relativity has to be used around massive objects, massive compact objects like black holes or neutron stars. If you're trying to make the most precise calculations of something, you might need to use general relativity. But for spaceflight, we can get along just fine with Newton's law of gravity. And even though it's the 21st century and we have had Einstein's general theory of relativity for over 100 years now, when we conduct spaceflight in the solar system, we still use Newton's law of gravity because it's a perfectly adequate description for our everyday lives, for the spaceflight that we're talking about here, the spaceflight that we typically do anywhere, whether it's low Earth orbit or exploring other planets. General relativity would only play a role in certain situations in astronomy. All right, what is Newton's law of gravity? So Newton's law of gravity says that between any two objects that have mass, and we'll call them body 1 and body 2, or mass 1 and mass 2, each of these bodies have mass, and there's a force of attraction between them. That force is measured in newtons, and that force is proportional to the masses of each of the bodies. That is, the force of gravity is the mass of the first body times the mass of the second body. But it also depends on the distance between them. And that seems to be common sense, right? If I take two masses and move them far apart, the force of gravity between them is going to be different, smaller than if the two of them are close together. An important thing to remember here is that the force depends on the distance squared. If I take two masses and I move them twice as far apart, the force of gravity between them is 4 times weaker because it's 2 squared. The distance, the force drops off as the distance squared. Now, sitting out in front of this equation is a constant of nature, g. G is a constant everywhere in the universe. As best as astronomers can tell, when we've looked at the universe as far as we can see in that direction, and as far as we can see in that direction, and as far as we can see in that direction, the gravitational constant g appears to be constant everywhere. It's constant everywhere in space, and it appears to be constant everywhere in time. You can think of it as sort of a fundamental property of our universe. But the other reason we have a g out in front of the equation, another reason we have that constant out in front, is because of the units that we're using. The unit kilogram and the unit meter, which we're going to use throughout this class, those are artificial human-defined constants. They're not what astronomers would call natural constants of the universe. They are, in fact, just numbers, just definitions that humans made up. Until recently, the kilogram was defined by a platinum iridium weight that's actually stored in the Bureau of Standards in Paris, France. And for a long time, the meter was defined by an actual meter stick that, again, was at the Bureau of Standards in Paris, France. And both of these were just invented by humans. And because humans invented these things, we need to throw a constant out in front. And the value of that constant g is 6.674 times 10 to the minus 11th newtons meters squared per kilogram squared. That's the value for g. Now don't worry, you don't have to memorize it. If you ever need it, you're welcome to look it up. If you need it on a quiz or an exam, I will give you a cover sheet that has not only the law of gravity, but also has the value for the constant there. An important thing, and this is worth writing in the margins of your notes right here, is that whenever you're using this equation, the masses have to be expressed in kilograms, and the distance has to be expressed in meters. A lot of times in astronomy, you will see distances expressed in kilometers, and you'll need to convert that to meters, because in this equation, mass has to be in kilograms, distance has to be in meters, and that's because of the value of g that we're using right here. Now, another important thing to keep in mind is, what do I mean by the distance? The distance between the two bodies is the distance from what center of one body to the center of another body. That is, we're measuring the distances going from the center of one to the center of the other. It's not the surface of this body to the surface of that one. It's the center of that body to the center of that one. You'll see here in a minute, when we calculate your weight on the surface of the earth, the distance that we use is not the distance from you to the surface of the earth. It's the distance from the center of you to the center of the earth. So keep that in mind, that the distance is measured from the center. And what we mean by the center, in physics, we would call it the center of mass of a body. We're not going to worry about that right now. Just know it's measured from the center of a body. So let's answer this question. Imagine an astronaut standing on the surface of the moon. How does their weight compare to their weight on Earth? So we're going to assume that this astronaut has a mass of 100 kilograms. And whether they're on the surface of the Earth or whether they're on the surface of the moon, their mass is 100 kilograms. But their weights will be different. And their weights will be different because the force of gravity is going to be different. The moon has a different mass than the Earth. The moon has a different size than the Earth. So the distances will be different and the masses will be different. So let's go ahead and do this for the Earth first. I said earlier, without demonstrating it, that an astronaut with a mass of 100 kilograms has a weight of 980 newtons. Let's calculate that now. So the force of gravity standing on the surface of the Earth, so this subscript Earth just means for right now to remind us that this is the force of gravity when they're standing on the Earth, is G times the mass of the first body and the mass of the second body, divided by the distances between the centers of the bodies squared. Now, in this case, I'm interested in the force of gravity between the astronaut and the Earth. So it's G times the mass of the Earth times the mass of the astronaut divided by the distance between the center of the Earth and the center of the astronaut squared. Now, a couple things to keep in mind. Doesn't matter which one you put first, right? Because in mathematics, 2 times 3 is the same thing as 3 times 2. You can do the mass of the astronaut first or the mass of the Earth first. Doesn't matter when we're doing multiplication. The distance here from the center of the Earth to the center of the astronaut is simply going to be the radius of the Earth, which is 6,378 kilometers. And that's because if we draw a picture here where we've got the Earth and the astronaut standing on top of the Earth, the distance from the center of the Earth to the astronaut is simply just the radius of the Earth. So let's plug some numbers in here and see what we get. G is 6.674 times 10 to the minus 11th. The mass of the Earth is 5.972 times 10 to the 24 kilograms. Again, that's not a number that I expect you to know. You can look it up if you ever need it, or again, on the quizzes or exams, it'll be on the front cover. So that's 5.972 times 10 to the 24 kilograms. We already said that the mass of our astronaut was 100 kilograms, and the distance between them is 6.378 times 10 to the 6th meters squared. That's because the radius of the Earth is 6,378 kilometers, but we need that number to be in meters, and to convert from kilometers to meters, we need to multiply by 1,000. So it becomes 6,378,000 meters, or 6.378 times 10 to the 6th meters. Now, we can plug all those numbers into a calculator. So 6.674 times 10 to the minus 11th times 5.972 times 10 to the 24th times 100 divided by 6.378 times 10 to the 6th. Don't forget to square it. That's a big mistake students often make, is they forget to square it. Plugging all those numbers in, we come that the force on the astronaut, a force of gravity on the surface of the Earth on the astronaut, is 980 newtons. That was the number I said at the beginning of the lecture. Let's do the same calculation for the moon. And let's think, how's this equation going to be different for the astronaut on the moon? Well, a couple things will be different. First of all, will the mass of the astronaut be different? No, because the astronaut's still going to have a mass of 100 kilograms on the moon. But the mass of the moon will be different. The moon is very much less massive than the Earth. And the radius of the moon will be different. And we'll have to use different numbers there. Now, here I've given you the numbers. The mass of the moon is 7.348 times 10 to the 22 kilograms. It's about 81 times smaller than the mass of the Earth. And the radius of the moon is about 1,738 kilometers, which is about, we usually say roughly a quarter the radius of the Earth. So now let's plug those numbers in and let's calculate the weight of the astronaut on the moon. So the force pulling on the astronaut on the moon due to gravity is G times the mass of the first body, the mass of the second body, divided by the distance squared. G is our constant. The first mass is the mass of the moon. The second mass is the mass of the astronaut. And the distance between them is going to be the radius of the moon. So that's where we get our distance squared. So now let's plug the numbers in. G is 6.674 times 10 to the minus 11th. The mass of the moon is 7.348 times 10 to the 22 kilograms. The mass of the astronaut is 100 kilograms. And the distance between them is 1.738 times 10 to the 6th meters squared. Don't forget to square it. And you work out the answer and you get 162 newtons. So the weight of the astronaut on the moon is 162 newtons, whereas their weight on Earth is 980 newtons. Another way to put that is that when you're standing on the surface of the moon, the force of gravity pulling on you is only 1/6 as much as when you're on the Earth. Because on the moon, it's 162 newtons. On the Earth, it's 980 newtons if your mass is 100 kilograms, and that turns out to be 1/6 as much. So the force of gravity on the surface of the moon is 1/6 the gravity of when you're standing on Earth. Now, turns out this is a useful thing because when the astronauts go to the moon, not only do they have their regular body mass, but they have to put those heavy suits on. And those heavy suits can weigh well over 100 pounds by the time you get the life support system, the backpack on, the helmet. The suit itself is quite heavy. So imagine on Earth having to carry around all that extra weight. It would make you very slow and very cumbersome. But on the moon, on the other hand, because you only weigh 1/6 as much as you do when you're on the Earth, that backpack, that suit only weighs 1/6 as much, and it's not a severe constraint at all. Now, as we'll see later on in the semester, the flexibility of the suit is a huge problem, but the weight of it on the moon is not. And just to put it in for those of you that prefer English units, just to, again, to put it in perspective, if you weigh 220 pounds on the surface of the Earth, you'd weigh only 36.5 pounds on the moon. All right, I want you to go out and get some practice with this one. On the quizzes and the final exam, I would expect you that you could tell me the weight of anybody on any planet in the solar system. Of course, I'll give you their mass, and I'll give you the mass of the planet and the radius of the planet. But I expect that wherever you go in the solar system, you should be able to calculate your weight. Now, since this is a class about mission to Mars, let's calculate it for Mars. What is the weight in newtons of a 100 kilogram astronaut standing on Mars? A couple things you'll need to know to work this one out is that the mass of Mars is 0.1074 times the mass of the Earth. That is, it's about 10% the mass of the Earth. The radius of Mars is about half the radius of the Earth. In fact, it's exactly, or it's close enough as 0.5325 times the radius of Earth. So I give you the mass of Earth here, 5.972 times 10 to the 24 kilograms, and the radius of the Earth was 6,378 kilometers. So go ahead and figure out, before you figure out the weight of the astronaut, go ahead and figure out the mass of Mars and the radius of Mars, and then use them to calculate the weight of a 100 kilogram astronaut standing on Mars. Now's a good time to pause the video, do all your calculations, put them into the lecture exercise, and then come on back and we'll work out the right answer. All right, let's work out the answer to this one. So what do we get? Well, the mass of Mars is 0.1074 times the mass of Earth, which is 5.972 times 10 to the 24 kilograms. Plugging those into your calculator, 0.1074 times 5.972 times 10 to the 24th, there's the mass of Mars. It's 6.414 times 10 to the 23 kilograms. So let's put that aside right now. We're going to need that in a minute. Let's calculate the radius of Mars. The radius of Mars is 0.5325 times the radius of Earth, which was 6,378 kilometers. So it's 0.35325 times 6,378. We get 3,396 kilometers for the radius of Mars. Now let's convert that to meters. 3,396 kilometers is 3,396,000 meters, or 3.396 times 10 to the 6th meters in scientific notation. Now that we know the mass of Mars and we know the radius of Mars, let's calculate the force of the astronaut standing on Mars. So the force of the astronaut standing on Mars, G times the mass of the first body times the mass of the second body divided by the distance from the center of the first to the center of the second squared. G is 6.674 times 10 to the minus 11th. The mass of Mars, we said, was 6.414 times 10 to the 23rd kilograms. The mass of the astronaut was 100 kilograms. And the distance between their centers squared was 3.396 times 10 to the 6th meters squared. And when you plug all those numbers into your calculator, you come up with 371 newtons. The weight of an astronaut on Mars, of a 100 kilogram astronaut on Mars, is 371 newtons. All right. So now the question is, go out to the lecture exercise and answer this. What fraction, percentage of that is that of their weight on Earth? So go ahead and calculate that. What fraction is this of their weight on Earth? All right, so how does that work out? Well, it's just the weight on Mars, which is 371 newtons, divided by their weight on Earth, which is 980 newtons. So dividing 371 by 980 gives us 0.379, which is 37.9%, or we're just going to round it to be a nice 38% when we talk about it in the class. So your weight on Mars is 38% of your weight on Earth. And again, this will be valuable when astronauts go to Mars because, again, they'll be wearing a heavy spacesuit with a life support system on the back. All of that will be quite heavy, but the weight of it will only be 40% of its weight on the Earth. Now, that's still significant compared to the Moon, where it's only 1/6. Here it's about, it's almost but not quite 40%. So just out of curiosity, because I want you to think about this, what is your weight on Mars in pounds? So I know most of the students in this class probably grew up in the United States. You're more familiar with using pounds than you are with measuring weight in newtons. So what is your weight on Mars in pounds? So ignore the weight of the spacesuit that you're weighing. And I just want you to think for a second, what is your weight on Mars? So go ahead and figure that out and then answer it in the lecture exercise. All right, welcome back. What did you get? Well, let's do it for me. In my case, my weight is about 250 pounds. So my weight on Mars would be 0.3789 times as much, or my weight on Mars would be about 95 pounds. So I weigh 250 pounds on the Earth. I would weigh about 95 pounds on Mars. So that's how you go about calculating your weight on other planets. You'll need the mass of the planet, you'll need the radius of the planet, but in the lecture exercise and the homework, you'll be calculating your weight on various bodies, and you should be proficient at that because there will be a question about it on the quiz. There will be a question like that on the final exam. So all right. So now let's talk a little bit more about the force of gravity and Newton's second law, F equals ma, and think about how those two are related to one another. In particular, I'm thinking back to that little video clip that we saw in the last lecture. I'm going to play it for you here again because it's just such an amazing video clip where Brian Cox works with some engineers at NASA.
This is NASA's Space Power
feathers
Facility near Cleveland.
and a bowling ball, and have the feathers and the bowling ball fall in the vacuum of space, or in the vacuum of a chamber, sorry. So let me go ahead and get this started here at 250.
Release. Exactly. They came down exactly the same.
So you'll remember in that last video that when they dropped the bowling ball and the feathers in a vacuum chamber at NASA, both the bowling ball and the feathers fall at the same rate. They accelerate down to Earth at the same rate. And I want you to answer this question then in the lecture exercises. So recall that video. How does the force of gravity pulling on the bowling ball compared to the force of gravity pulling on the feathers? Is the force of gravity on the bowling ball greater than the force on the feathers, less than the force on the feathers, or equal to the force on the feathers? So go out there and answer that question in the lecture exercise and then come back in a few seconds. I'll spend my time petting Gizmo here. All right, so what did you think on this one? What did you get for the force of gravity? I think for sometimes when you're first starting to think about the force of gravity and forces and accelerations, you have to be very careful to differentiate force from acceleration. Because I think a number of people, when they're asked this question, say, well, the two of them fell at the same rate. The two of them hit the ground at the same time. So the force must be the same on the two of them. But of course, that can't be true, right? Because the feathers have a lot less mass than the bowling ball. And because the feathers have less mass, if the force acting on them was the same, the feathers would undergo a greater acceleration. Remember, F equals ma. And so the acceleration that a body experiences is the force divided by the mass of the object. And if the feather and the bowling balls were acted on by identical forces, then the feathers would experience more acceleration due to their smaller mass. And that means they would accelerate faster than the bowling ball does. So how is it then that the two of them fall at the same rate? The force of gravity tells you right away that the force acting on the bowling ball has to be greater, right? Because the force is G, mass of the Earth, times the mass of the body. And so the mass of the bowling ball is clearly greater than the mass of the feathers. So the force of gravity acting on the bowling ball is greater than the force of gravity acting on the feathers. So if the force acting on the bowling ball is greater, why did they hit the ground at the same time? Well, remember, what matters is their acceleration. And remember that property of mass. Mass is also a measure of the resistance to acceleration. Although the force of gravity is pulling stronger on the bowling ball and pulling less strongly on the feathers, that bowling ball has a lot of mass, and it's harder to get moving in the first place. It has much more inertia. The feathers are easier to get moving in the first place. What we really need here is to calculate the acceleration due to gravity. So the acceleration due to gravity is simply the force of gravity divided by the mass of the object. So let's work it out and see what that is. Force is mass times acceleration. The acceleration due to gravity on the surface of the Earth is the force of gravity divided by the mass of the object. The force of gravity, we've already seen that. That's G times the mass of the Earth times the mass of the object divided by the distance squared. So the acceleration due to gravity is the force of gravity, G, mass of the Earth, mass of the object over distance squared, divided by the mass of the object. And here's what's amazing. You'll notice that the mass of the object in the bottom and the mass of the object in the top cancel one another out. And what we're left with is that the acceleration due to gravity is just G times the mass of the Earth over the distance from the center of the Earth to the surface of the Earth, the radius of the Earth squared. It doesn't depend on the mass of the object. That's why they fall to the ground at the same time, because the acceleration that they experience is identical, because the acceleration doesn't depend on the mass of the object. The force does. The bowling ball is experiencing the greater force, but it's also more massive and it's harder to get moving. And those two cancel one another out. So that ultimately the acceleration just depends on the mass of the Earth and how far it is from the center of the Earth. So now let's talk about weightlessness. Go back to our idea of weightlessness for a second. So I interrupted weightlessness to talk about the law of gravity for a few minutes, but let's go back and discuss weightlessness. Why are astronauts weightless? The common misconception is that astronauts are weightless because there's no gravity in space. And as you can already see from Newton's law of gravity, of course, as we saw with the question about what keeps the space station in orbit around the Earth, is that its gravity keeps it in orbit. Those astronauts are subject to a force of gravity strong enough that even though they're moving at over 17,000 miles an hour, that force of gravity holds them in orbit. What is the force of gravity? Let's calculate it. Let's calculate the force of gravity on an astronaut on the surface of the Earth, so down here on the surface where you and I are. And then we'll do the same thing for an astronaut in orbit, and let's see how they compare. Now, your first thought might be, well, in orbit, they're much farther away from the center of the Earth, so the force of gravity is going to be a lot smaller out there. But let's think about it for a second. Sitting here in my chair in my office, I'm 6,378 kilometers away from the center of the Earth. An astronaut in orbit is 422 kilometers above the surface, which means they're 6,800 kilometers from the center of the Earth. Now, those two numbers are clearly different, but just looking at them, you're going to say to yourself, hey, now, wait a second. They're not that much different from one another. The force of gravity acting on the astronaut, it's not going to be that much different than the force of gravity acting on me on the surface. But let's do the calculation and see what we get. What's their weight on Earth? We've done this one already, so I'm going to go through it fairly quickly. The force of gravity for the astronaut standing on the surface of the Earth is G times the mass of the Earth times the mass of the astronaut divided by the distance between the center of the astronaut and the center of the Earth squared. And since they're on the surface of the Earth, that's just the radius of the Earth. So the force, 6.674 times 10 to the minus 11th, times the mass of the Earth, 5.972 times 10 to the 24 kilograms, times the mass of the astronaut, 100 kilograms, divided by the distance between the center of the Earth and the center of the astronaut, the radius of the Earth, 6.378 times 10 to the 6 meters squared. You do the calculation, you get 980 newtons. Now, let's move that astronaut 422 kilometers up above the surface. Now what do we get? Well, let's think about what's going to change and what won't change. G is not going to change. The mass of the Earth is not going to change. The mass of the astronaut is not going to change. The distance is going to change, but it's not going to change by very much. So let's see what the calculation looks like now. So here it is when they're in orbit. So first of all, if I flip back and forth between these two, you'll see not much changes. The only thing that's changing here is the distance, if you take a look at that, right? So let's do it when they're in orbit. It's G times the mass of the Earth times the mass of the astronaut over the distance squared. 6.674 times 10 to the minus 11th. Mass of the Earth, 5.972 times 10 to the 24 kilograms. Mass of the astronaut, 100 kilograms. This time, they're not 6,378 from the center of the Earth. They're 6,800 from the center of the Earth, or 6.8 times 10 to the 6th meters. Always don't forget to square it, and you get 862 newtons. Now, on the surface of the Earth, their weight is 980 newtons, and you can see those two aren't that much different. So when they're in orbit, the force of gravity acting on them is slightly smaller than when they're on the surface of the Earth. And in fact, it's about 88% of the force of when they're on the surface. So if there's that much gravity acting on them, 88% of the gravity that they have here on the surface of the Earth, why are they weightless? And the answer is they're weightless because they're falling. So let's take a look at what I mean by that. So here's an example, an elevator example. So imagine for some crazy reason you go to a hotel that has a really fast elevator in it, and you bring a bathroom scale. And in fact, physics teachers have done this over the years, and they've had students bring bathroom scales on elevators. You can find some funny videos of it on the internet. But basically, imagine you take your bathroom scale and you put it in the elevator, and then you stand on your bathroom scale. And what are you going to measure? Well, you're going to measure the normal force, the regular force that you're pushing down on the surface of this. You're going to see, in this particular case, for this individual, it's a little bit less than 140 pounds. Now, what happens when the elevator accelerates upwards? I'm not talking about moving upwards. I'm not talking about moving upwards in a constant speed. I'm talking about accelerating upwards, where you're constantly moving faster and faster and faster. If you're accelerating upwards, that means there's a force being applied, right? The elevator is pushing up on your feet, which means your inertia, the fact that you want to sit still, is going to push against that. And you're going to push a little bit harder against the floor of the elevator. And in fact, if you measure your weight on that scale, when the elevator is accelerating upwards, you'll notice that you weigh a little bit more than 140 pounds because the elevator is accelerating upwards and it's pushing harder on your feet, and your inertia wants you to get left behind, so you're getting squeezed into the floor and you're pushing on that scale a bit harder. Now imagine what happens if that elevator goes down very rapidly. And we've all probably been in a skyscraper at some point where you've been in one of those express elevators that goes down very quickly. And as the elevator accelerates downward very quickly, you get the feeling of butterflies in your stomach. And you get that because as the elevator accelerates out from under your feet, which are pressing on the elevator floor, as that elevator floor accelerates out underneath from you, you get left behind. But as you can see here, you weigh a little bit less. So if you normally weigh a little bit less than 140 pounds, as the elevator is accelerating downwards, you'll weigh, say in this case, less than you did before. Now imagine that we cut the cable on the elevator. All right, so the cable cuts. Now the elevator box is falling. We're going to ignore all the safety mechanisms. All the modern elevators, right? They have lots of safety mechanisms. If the cable were to ever break, there are braking systems that'll bring the elevator to a halt fairly quickly. Let's not worry about all those right now for a second. But when you break the cable on the elevator, what's going to happen? Well, the box is going to fall to the earth. It's going to accelerate down to the earth due to gravity. Well, remember, the acceleration doesn't matter what doesn't depend on the mass of the elevator, doesn't depend on what the elevator is made of. The acceleration is 9.8 meters per second, 9.8 meters per second squared, regardless of the mass. So the elevator is accelerating downwards at 9.8 meters per second squared. But you're accelerating downwards at 9.8 meters per second squared. And because you're both accelerating downwards at the same acceleration, you're going to float weightless inside the elevator. If an elevator cable gets cut while the elevator box is falling to the ground, you are floating weightless inside the elevator. And you're weightless because you're falling. And sometimes we call weightlessness free fall because you can be weightless by falling. Now, there's a couple ways you can experience this. The easiest way to experience this is to do something like King's Dominion. Right here in Virginia at King's Dominion, they have a ride called the Drop Zone. There are lots of these around the country, so you may have gone on a similar thing at another amusement park someplace. Basically, what they do in the Drop Zone is they strap you into a seat, they lift this ring high up into the air, and then once it gets all the way up to the very top up there, they hold it there for a couple seconds for you to get really, really nervous, and then they let it go. There's two big clamps that unclamp, and they just let it go. And what I mean by let it go is exactly that. They just let it go. And it falls to the ground. It accelerates to the ground. It accelerates at 9.8 meters per second per second. Now, first of all, if you've never experienced free fall like this, I can tell you from having ridden the Drop Zone one time, it's extremely disconcerting because after 1 second, you're going 9.8 meters per second. After 2 seconds, you're going 9.8 meters per second, and you gain another 9.8 meters per second so that you're traveling almost 20 meters per second downward. In the Drop Zone at King's Dominion, you fall for about 2.5 seconds before they finally put the brakes on and slow you down so you have a nice gentle landing.